we're going to examine the stability of solutions of a certain differential equation. It's a second order differential equation, and this is it up here. And it's basically the differential equation for harmonic motion. This a of t here is what makes it a little different. If that were 1, then in fact the solution to this would be harmonic motion or circular motion. And what I've got here is a program that takes the differential equation and solves it numerically. You plug in the parameters for the function a of t basically, and I can click on these buttons and plug in different parameters, and I click this button and it generates a solution to the differential equation. It does it numerically. It's approximate, but it's a pretty good approximation. And as I said, this differential equation is really just the equation for harmonic motion if that a of t is 1. So let's look at that first just to sort of orient ourselves. Well, here a of t is 1, and I've set omega to 1, although in this case it really doesn't play a role in anything. So let me generate that path. I've already done it. It's down here, and you can see what the result's going to be. So I'm doing 10,000 iterations over a time period of 4t, and the period for this thing is 6.28. And it generates this as a result. There are actually two functions being represented here, a red one and a blue one. They're both the same, or at least they follow the same path. They're 90 degrees out of phase with one another, so they are independent of each other. All right, now let's look at a different case. Let's let a actually be something. So here we're saying omega is 7, and a of t is this thing here. So that is periodic, and a period is given by 2 pi over omega, so the period happens to be 0.90 in this case. So let me hit my button and see what path that generates, what solution it generates. Takes a second or two. And there it is. These paths down here are the solutions. There are actually two solutions being generated, a red one and a blue one. And the first red point is the starting point for one solution, and the blue point is the starting point for the other solution. And I've set things up so that they start at 1, 0, and 0, 1. So this means that the fundamental matrix that these paths represent is actually the principal fundamental matrix. And that's important in the development, because otherwise the equation we have ultimately for phi wouldn't be as simple. So it's important that they start out at 1 and 0. And let's just check that. If I make my time equal to 0, the fundamental matrix, which is over here, should be the identity matrix, and it is. So everything is working okay so far. Okay, now how do we study the stability of this solution? Well, we want to know whether it shoots off to infinity, converges to 0, or is periodic, basically. Those are our choices. And looking at it, it certainly looks like it's shooting off to infinity, but let's see why that is. How do we do that? Well, we take our x, and I'm just going to go to this quickly so I'll cover it in class. Take our x, we evaluate it at the period t, and we get the matrix B. And over here, these 2 points actually represent B. I'm evaluating the first solution at time big T. I'm evaluating the second solution at time big T, and then I'm putting that result in. This is the first solution at time big T, and this is the second solution at time big T. Then I calculate my phi, which is the solution of the characteristic equation. I won't go into that, and right now I'm presuming you're familiar with that. But this is our definition of phi. Again, this was done in class, where my u is the first solution. I don't like using the exponents for these functions. It's just too hard to type. So u is my first solution, and v is my second solution. So if I were to look at my x and see what the formula is in there, let's see if I got this right. Yeah, that is how you put together your fundamental solution in this special case. You take your first function and its derivative, and your second solution its derivative. That's my fundamental matrix. All right, now this is our case 1 for stability. So case 1 is concerned with when phi is a positive number. And notice what happens when phi is a positive number. The two eigenvalues of B, that's what these things are, the two eigenvalues of the matrix B are also positive numbers. And one of them is going to have to be greater than 1, and the other one is going to have to be less than 1. Now, why does this one have to be greater than 1, for instance? Well, let's take a look at it. It's pretty clear from this that if phi is greater than 1, then phi plus something is greater than 1. So that's why this is always going to be greater than 1 here. Now, what about this one here? What do we know about this one? This one actually turns out to always be between 0 and 1, and the reason for that is, remember this fact that if you multiply the two together, you're going to get 1. The product of these things is always 1, not just in this case, but in every case. So that means 1 is the reciprocal of the other. So if one is greater than 1 and positive, then the other one has to be less than 1 and positive. And now this comes about right from the definition of row 1 and row 2. Let's just a little review here. Just to remember how we define row 1. That's that, and row 2 is that. And if you multiply those out, you're going to have some canceling, and it turns out to be just 1. So let's do that as long as we've gone this far. Let's multiply that through. And now this thing here, this is the square root squared. So if I get rid of that square root, that's going to just be phi squared minus 1 pops out. So, and there it is. So that product is always 1. So that's why we can say that one of these eigenvalues is greater than 1 and the other is less than 1 and positive. So what does that mean as far as stability is concerned? Right away we've answered the stability question. If ever the modulus or absolute value or the norm, whatever you want to call it, of the eigenvalue is greater than 1, then the solution, corresponding solution, shoots off to infinity. Now that's this red solution over here. It's shooting off to infinity, and the other one, its modulus is less than 1. That means it converges to 0. So this is always going to be the case for row positive and greater than 1. It has to be greater than 1. If it's not greater than 1, then these don't come out to be real numbers. And we'll see that in case 3. They come out to be imaginary numbers. And it's pretty clear from looking at the definition of phi why that's so. So let's think for a second. What else do we want to say? All right, let me review how we get these secondary solutions. Remember, x of t is a fundamental matrix, and x2 of t is also a fundamental matrix with a different set of solutions. And we get that set of solutions by taking the eigenvectors of B. Let me do that a little better. We take each eigenvector of B and multiply it by the first fundamental matrix, and that gives us a second solution. And we do that again down here with the other eigenvector. And there's solutions. Any linear combination of the columns of x is a solution. And the reason we do that is that now we can, this solution has a very particular property. It's not periodic, but it has the property that every time you advance little t by big T, it throws out a row. It throws out an eigenvalue. And that fact is used to make this true over here. That guarantees that if we define P1 in this way, it's going to be periodic. So when we're all done, we put our two solutions, x of t and y of t, and again they're over here. This is x of t shooting up to infinity, and this is y of t converging to 1. We put them together as columns in x2, and that's our second fundamental matrix. And it's pretty clear from the way we've defined things that now x2 is the product of p and y. And let's actually look at that. These are some of the things we should be checking as we go along here. Let's look at a few of these. That should be 1 there. Okay, the reason is because the acceleration is not really defined right at the initial point. There we go. Now, these should all be 1. If they're not 1, something is wrong. So what am I checking here? First of all, I'm checking to see if my eigenvalues are doing the right thing. And the 1 over here says yes, the equality is true, at least out to 2 places of precision. And the second thing that this is checking is whether the p's I've generated are periodic. And the Wronskian should be 1. Again, that's all discussed in class. And this is somehow the most basic equality that has to be true. Our fundamental solution has to satisfy that equation. And our second fundamental solution has to satisfy this equation. What we're trying to do here in this stability analysis is to find a fundamental solution that we can break up into a polynomial solution and a multiplier solution. The yt is the multiplier solution, and that tells you about the stability. That's this down here, and just looking at the elements in there, you can tell whether it's going to diverge or converge or be periodic. But that depends on these eigenvalues, the mu1 and the mu2. Alright, what else is in here? Okay, well, we put our p's together in a matrix big P, and of course that should be periodic too. And here's the equation that makes everything work for our x's. We define our x's down here to be x of t times v of 1, and now that makes them not periodic, but it makes them so that they throw out a row, they throw out an eigenvalue every time you advance t by big T. And that's the same for the y also. And one thing we always want to check is that our periodic solution is real valued. In this case, it has to be. If we look at our definition of the periodic solution, that's here. Again, I'm assuming that you're comfortable with a lot of this. Mu1 is real. Look at it up here, and it's real because rho 1 is real. And rho 1 is real because this is positive and greater than 1. That's how everything traces back to this being positive and greater than 1. If it weren't greater than 1, this might be, well, this could be I guess it could be imaginary. But anyway, this would be imaginary. And if that's imaginary, then this thing down here is going to be imaginary, and you're going to have a problem if you don't like imaginaries. So where am I in all this? There's a lot of boxes here. All right, so the point I'm trying to make is that P1 and P2 are real, and that's good. That's the way we want them to be. And let me say one more thing about all the pieces here. I'm going to be looking at all these pieces in future cases, even though in this case we didn't have to look at nu1 and sigma1. Let's get used to them, and actually, they tell you something here even though we didn't use them. Nu1 is the real part of mu1, and sigma1 is the imaginary part of mu1, likewise over here. And since mu1 is a real number, nu1 is positive and sigma1 is 0. The imaginary part is 0. And that's significant. That looking at these, that tells us about mu, and the fact that mu is real means these things down here are real, which we want them to be. So that's why it's important to kind of scope out mu and its pieces.